Behind those three letters, there is a world of knowledge and creativity that can make your life easier and our industry more and more competitive domestically and abroad. CIT, SENAI Innovation and Technology Center, is a group of institutes created with the commitment to offer solutions for the great challenges of the future. With 3 innovation institutes and 5 technology institutes gathered in a 120,000 square meters campus, CIT offers knowledge in the mining, steel, and automotive industry, as well as in the food and beverages and textile industry. Wherever there is a demand for technology and innovative solutions, there is the work of technicians, researchers, academics, and hundreds of specialized professionals spread throughout 70 laboratories with state-of-the-art equipment. CIT SENAI offers a range of services approved by Inmetro and by renowned state and national agencies. They reinforce our commitment to quality standards for laboratories, ensuring excellent service and greater competitiveness for all our customers. There is a world of business opportunities within CIT. Here, ideas become reality for researchers and industries through innovative projects, applied research, and the development of innovative solutions that create new ways to boost the economy. Training courses are created on demand in several fields of knowledge for specific industrial services. We serve industry through trials, collaborations, operational and inspection services, and we offer consulting services in a variety of knowledge areas. In addition to housing important partner institutions within our campus. Ideas that spark new opportunities, challenges that generate results. For large, medium, and small companies, CIT offers technological solutions capable of transforming business into important achievements. Knowledge, innovation, and cutting-edge technology, assisting the development of industry and society. CIT, SENAI Innovation and Technology Center, where the future of the industry is here, now.
Hello, everyone. Good morning to Brazil, good afternoon, and good evening to those joining us from the other parts of the world. Welcome to our webinar, Microstructural Characterization Applied to the Steel Industry. My name is Nacy, and together with my colleagues Eduardo and Clélia, we will be your moderators throughout today's webinar. We are part of the Research, Development and Innovation team at the SENAI Institute of Metallurgy and Special Alloys. First of all, I'd like to thank all of you for joining us today. I'd also like to thank the entire SENAI team for their support in organizing this event, as well as our invited speakers from Aachen University and Vallourec company. Today's webinar will last approximately 2 hours and will feature 3 distinguished speakers representing both academy and industry, all of whom have made significant contributions to the global steel sector. Before each presentation, we will briefly introduce the speaker. Each presentation will last approximately 30 minutes. At the conclusion of all presentations, we will have approximately 20 minutes for a live question and answer session. We encourage everyone to submit questions throughout the presentation. Use YouTube chat. Our moderation team will select the questions and direct them to the speakers during the Q&A session. To help us organize the discussion, please include the speaker's name at the beginning of your question. Now, it's my pleasure to introduce our first speaker, Dr. Anderson Caires. In this presentation, he will explore about microstructure characterization applied to the steel industry. Dr. Anderson Caires is a physicist with a PhD in metallurgical and materials engineering from Federal University of Minas Gerais, where he also completed a postdoctoral residence. Alongside his scientific background, he earned 2 MBAs, one in strategic management of innovation and intellectual property, and another in strategic project management. Today, he works as a technology analyst at the Center for Innovation and Technology, leading the Microstructural Characterization team at the SENAI Innovation Institute for Metallurgy and Special Alloys. Anderson, the floor is yours. Please go ahead and begin your presentation. You have 30 minutes. Have a great presentation.
Really nice. Thank you, Nancy. Thank you so much. It's wonderful to see so much people from around the world joining us for our webinar. Thank you for everyone. I'd like to say thank you for our speakers, for sharing the technologies issues in this morning here in Brazil. Thank you so much. This webinar is a part of series of technical webinars on the topics that matter to the steelmaking industry, connecting academia, industry, and research centers to share technology and build new partnerships, really important for us. I'm Anderson Caires. I lead the Microstructural Characterization facilities at SENAI Institute of Innovation in Metallurgy and Space Alloys here in Brazil. And I have most of my career looking at materials so closely, trying to understand why they behave the way they do. I believe we need to understand the material properties, thinking for the new applications, thinking how we can improve the properties for industrial applications. So, in this talk, I will give you a quick roadmap about microstructural characterizations and why matter for today's steel AIG research. I think we need to understand the phenomena and the correlations between the microstructures, properties, and performance of metallic materials. And then I will share a few real cases, few examples for our institutes, some papers for our team, as examples for applied research, and how these characterization techniques can be used in real-world industrial challenges. And finally, I give you a look for the SENAI Institute of Innovation, Metallurgy, and Special Alloy research capabilities, just to get a sense of kind of work we do and how we can help in our challenges. So let's get started. All right, I want to start with the basic. Steel is everywhere, in every aspect of modern human society. Global steel productions and data for 2024 is around 2 billion tons per year. That is a lot. That is more than any other material produces in this planet. It is building we work in, the car and train we travel in, the pipeline that carry energy across the continents, in our homes, and the tool in our laboratories. And I think we need to understand what happens inside of these materials at micro level. This is really important to real-world applications. When you're talking about the material produced and used in these magnitudes, every small improvement in how we can understand the microstructure and control the microstructure have a great influence in performance and great economic impacts of materials for society. Maybe we can understand the grain size control, the phase distributions, inclusion contents, the precipitation behavior. All of these things is really important for applications for society. Okay, so here we have a really single image of a common steel microstructures. It's a very simple metallographic image. But for a scientist like me, it's so beautiful. It's really interesting. It's my background in computer, so we can see grains and grain boundaries and fair height and pair height. So it's just really interesting. It's really beautiful for scientists or metallographic technicians in the lab every day. But we can see what's behind materials using our eyes, or maybe using simple microscope. Things like metallographic orientation, fine precipitation, and so on. To explore these beautiful material properties, we need to use more specialized techniques. So let's zoom in. You can see the full range of level when you're talking about the microstructural characterizations. This is a trip between the macro level to individual atoms. And the macro level, okay, we can find the classical phase we expect finding steel. The ferrite, the BCC structures, perlite, the mixture of ferrite and cementite, just the slides on shown a moment ago, the binites, martensites, austernites. So these beautiful structures why we start seeing in laboratories every day. But we also keep a close eye in things like grain boundaries, both in high and low angle, twins, non-metallic inclusions. All of these things have a bit to say about the material behavior, the mechanical properties of materials, the application of these materials. As you move to the nano level, the picture gets a little more interesting. This is where we start to looking at the texture of material, the crystallographic orientations, maybe using MAPE out, using EBSD techniques, for example, nano precipitations in the atomic scale, maybe some really small precipitates in 5, 6 nanometers. It's a really small, but orientation conditions between these precipitates and materials have a great impact on mechanical properties of materials. It's so interesting. In this finest level, in the atomic level, we're talking about locations, the fact in crystallography. It's a so beautiful science behind a single piece of metal. So why did I want to show you these pictures today? The reason is actually very simple. Steel is a really complex material. And we need to have a multi-scale picture of steel microstructure for micro level to atomic level together in the single map. At macro scale, we are looking for grain structures in morphology, maybe crystallographic textures, segregation bands, inclusions, non-metallic inclusions, and maybe deformed regions. We need studying this in the micro level. Moving to the more level of magnifications, you get to the phase distributions. Okay, I like to see the ferrite, perlite, binite, martensites, beautiful imaging using SEM, austenites, and explore the precipitations. All of these pictures tell us about the materials processing history, and maybe your applications and possibilities for applications. And the nano thing variants, subgrains, dislocation shells, twins, deformations. It's really, really complex figure. And the nano started resolving nanoprecipitates, like I said before. The coherence between precipitating matrices is so important. The interface between matrices and precipitates is important, and you need to use electron diffraction to explore this. And these atomic scale materials have a lot to say about the materials applications, the material possibilities. And this, for me, is really a mental mode I want to show you this morning. Because I think every characterization technique we use today is just a way to access one or maybe several of this level. In fact, you need a combination of techniques to explore these two microstructures and correlate its properties and material performance. This slide illustrates one central concept, and I think for modern material science and modern steel science. So, Here I say, no single characterization techniques can completely describe the steel microstructure. Instead, we need a multi-level, multi-scale and correlative approach, where if analytical techniques provide a complementary information across different levels of materials. Moving to the macro, maybe the macro using optical microscopy in our metallographic lab to understand the morphology of grains distributions, phase distributions. It's a really interesting, more simple way to explore the metal surface. This is interesting. Things, for example, seeing the segregation, the macro segregation and inclusion distributions. It's okay. It's a very single characterization techniques. And moving for more complex, for example, we need to know the composition of material using maybe optical emission spectroscopy and X-ray fluorescence, for example. And then to moving for more complex characterizations, we need to understand the crystallographic textures and grain orientations of material using EBSD, for example, in SEM. EBSD was the more interesting characterization techniques for steel. And the micro, moving to the micro, we begin to resolve individual phase and microstructural constraints. Here, scanning electron microscope SEM become a primary tool. Imagine for the grains, identification ferrite, perlite, bainite, these beautiful phases that you're working every day in our laboratories. Maybe using for image for inclusions and nano in dimensions, the formation features of the material in high spatial resolutions. And of course, SEM is commonly combined using LDS or WDS to determine elemental compositions or specific phase or inclusions. We can use, for example, X-ray fractions, XID, to identify crystalline phases and quantificate crystalline fractions. This is really important characterizations for performing a piece of steel. At the submicron, this is really interesting, the submicron and nano. You enter the domain where the mechanisms originates is really interesting. And here we need to use the more advanced technology. The high resolution transmission electron microscopy, for example, for direct observations of nano precipitations, the martensite lights, maybe dislocation structures, twins, subgrain boundaries. It's really, really interesting to see this level of modern characterization techniques of the metal surface of metal. But another more technology for these days using atomic scale, for example, atomic tomography. It's great to analyze the metal. This is three-dimensional new atomic resolutions to quantify, for example, solute segregation, clustering, precipitation chemistry. It's really, really nice using the atomic tomography to explore the material properties, to explore the microstructure of materials. And of course, we need another complementary techniques to explore the material. Okay, the mechanical testing is so basically we need to understand the mechanical property of materials. We need geometry for understanding the property of materials, but using computing of simulations is another really, really interesting things. Simulating material properties using computational techniques, maybe in confound, maybe in more modern machine learning, AI could help you understanding property of material. It's really interesting. These correlative techniques, combine all these techniques, we can have a full picture of your sample. And this technology we use to create new applications or maybe increase some performance of materials in one industry. Maybe just 0.5%, maybe 1% of improvements of the material dimensions is so big, have economic impact for society. This is a panorama for materials characterizations in these days, a lot of techniques. So this is not a talk about more specific of each technical aspect of these analytical techniques, but it's a more general approach to use these techniques to analyze material. Here in our institutes, we have been working with our industrial partners and projects to understanding the relationships between microstructure, properties of material, and performance. It is really interesting. Not just create new composition of materials, but understanding the material properties. Here, we can show 3 examples of papers was published together with our partners to understanding microstructure of materials to resolve some real challenging for industry. First, we have an interesting work together for our colleague Daniel Matsubara for Gerdau Company, one of the largest steel makers in the world, in Brazil. The challenge here was to understanding the influence of fine vanadium precipitates on the mechanical properties of steel for structural applications. This is really interesting example. These are working collaborations between the Daniel Matsubara, team here at SENAI, and the Professor Victor Wolff and Federal University of Minas Gerais, and try understanding why they observe the different mechanical properties and for applications. We have performed every level of characterizations and optical microscopy in maybe SEM, it's a great image of CM, GM, to analyze really small precipitates. This image on the right, it's a replica we're extracting the precipitates for the surface of a metal in the film of carbon to analyze these precipitates. And we find the orientation relationships. The materials and precipitate interface was really important to understanding the difference observed in mechanical properties. And then we use the electron diffraction to confirm these precipitations interface the following the Birkenuke orientation relationships. This is just an example and the situation you need to use a more advanced transmission microscopy technology. Okay, this is very hard work to prove the orientation conditions between really small precipitation and the matrix of metal. This is really interesting for industrial application. Another example of microstructural characterization have playing a main role, a central role, was our work with a company Vallourec, for my colleague Roberto Maranhão, José Roberto, and Vicente Trindade, one of our speakers this morning. In this work, we're using the Global Thermomechanical Simulator to reproduce a well thermal cycles and comparing in the simulate sample against the real well samples. Again, the multi-technique characterization approach using this work in optical scanning, electron microscopy, using several different techniques for mechanical characterizations of materials. And overall, the physical simulations reproduce the microstructures, and you compare the real-world scenario to give a confidence in our simulations using the Global machine. Global machine is a beautiful machines to explore the metal properties. There is one paper for the last year for Roberto Maranhão in Pipeline Logistics Journal. It's a really interesting work with our Vallourec colleagues. And finally, I have a third example of paper and characterization works my team in SENAI and another institutes for here SENAI have working in industry to analyze the microstructure. This is 2 papers present my colleague Ricardo Nolasco, 2014, and ICE Steel in China. And this is a project between CIT and CBMEM and a company for producing nióbio here in Minas Gerais, and maybe I think it's the largest nióbio producer in the world, to explore the challenge in microstructural control in seamless pipe productions. This is a really two interesting papers. We send these papers for attending after the webinar, and this works. You explore how the precipitation behave along the holding process. This is really interesting papers and to explore these really interesting phenomena, trying to improve the material properties for applications and maybe new applications for these materials. We analyzed several still in this project. So these are just three single published papers in the literature as an example of kind of research we have performed here in SENAI and today. And I would like to give you some context about SENAI network. Now, SENAI is 28 Institute of Innovation spread across Brazil, each one focused at a specific technology area, alignments for the need for local industry. Here at Minas Gerais states, Minas Gerais means maybe English general mining, because I study for mining here in our states. We have three SENAI institutes and surface engineering near here for our institutes, the metallurgy, special alloys, and minor processing. All of these institutes have working together for industry for understanding the challenges for the industry, create a new process, new products, and trying to help the industry in your everyday challenges. But across Brazil, we have a lot of other institutes and advanced manufacturing in São Paulo, for example, and maybe nanocomposites, polymers. I have a lot of different areas of expertise distributed across the Brazil territory. Here at Minas Gerais, we have our Innovation Technology Center. It's a big campus here in the city of Belo Horizonte. We have now two campuses. In fact, we have our campus here in Belo Horizonte and another campus in City Lagoa Santa, near here in Minas Gerais. We explore the hard earth technology. Our campus have now 8 institutes of innovation technology for SENAI. We have more than 100 employees here dedicated for industrial research. We can explore our campus using these QR codes here. Maybe please feel free to explore our laboratories, our beautiful campus here in Belo Horizonte. And would like to everyone to visit our company, our campus in the future. The SENAI, it's a really complex. We have a lot of different area of expertise here in our campus, not just in metallurgy and special alloys, but we have another area of expertise in minor processing, surface engineering, automotive companies. We have one of the more modern labs of automotive testing in Brazil here. And we have our decarbonization center. This is really important for us because we believe that's really important to move society for more sustainable way. It's really interesting. And hard earth for technology is a hot topic today. It's really important for the future technology. And we have now our campus focus on hard earth research and applications in Lagoa Santa City here near the Belo Horizonte. Our institutes, we have focus in metallurgy and special alloys. We have clients in steelmaking industry and alloy companies across Brazil. Automobile companies have created new kind of steel for automotive applications, for example. Oil and gas company. We have the 3 main areas for expertise and new metallic alloys, metallurgical process, and a new area for additive manufacturing here in our campus. It's our core of expertise here at the SENAI Institute of Innovation in Metallurgy and Special Alloys. And then we have top awards research facilities here. For example, alloy design. We have we using computational simulations to understand the material properties and to design new alloys, both and ferrite and no ferrite alloys. And we have a laboratory to alloy meeting and remeeting using vim furnace and remeeting using var furnace. And here in our campus is a pilot plant for 100 kilograms lingot. And of course, we have the complete microstructural characterizations. It's a world-wide metallographic laboratory here, and maybe you have a part of electron microscopy, scanning and transmission electron microscopy, and how we have a team for process and metallurgical process and heat treatment, mechanical testing, and so on. And the big teams here, and the city in easy metallurgy and special alloys. We have supporting industry using R&D grants for the several national and international possibilities for help the industry in your challenging and everyday challenges. So, and we have here on the campus some partners, residents here inside the campus, like some company like Celor, Embraer, and big companies in Brazil can visit in campus because the proximity is really important for the science. So this is our institutes. In general, in general, I would like to invite everyone to know a little bit more about our institutes and our possibilities that you can to help industry in everyday challenge. And this is our team here at the SENAI and the Metallurgy and Special Alloy Institutes. That's our colleagues here and great colleagues. So I think it's always in the team we can achieve more together. And the team has working very hard every day to help industry in your challenges and making new technology for industry. And then we have these last slides for our characterization team here at the city. The team is full dedicated for everyday challenging materials characterizations. It's so hard. Material characterization is so interesting. It's so beautiful to understanding every day. I have the team dedicated here for materials characterizations, and it's great here. So thank you. So our attendance, and thank you so much, everyone. I would like to invite you to connect, to share your challenging views, talking about how we can help you in your challenge. And you move into our next speaker, Dr. Alexander, to explore a little bit more applications and automotive industries. Is way great research work making in Germany in these days. So thank you very much. Nancy, back to you. Thank you.
Okay, thank you, Anderson, for your excellent presentation. We will now move on to our second presentation. It's my pleasure to introduce Professor Dr. Alexander Gramlich, who will present on understanding Tramp element effects in automotive steels. Dr. Alexander Gramlich is a research fellow and the chief engineer at the Steel Institute at Aachen University in Germany. His research focuses on sustainable material design, circularity, and the development of high steel performance. He leads the Steel Materials Design Research Group, and he has resolved the Otto Kiesel Award 2021 and the VAEH Award 2025 for his contributions to the steel industry. Professor Alexander Gramlich, please feel free to start your presentation. You have 30 minutes. Have a great presentation.
Thank you very much for the kind introduction. I'm very happy to speak here today and give you our opportunity or our opinion on Tramp element effects in automotive steels. It was a perfect introduction by Anderson. I'm very happy that you gave such a nice overview of microstructure. So this eases my job quite dramatically now to explain you what we are doing. As you can see here, I have a double affiliation at the moment. I'm also the managing director of a new DFC research training group, which we started this year, and I will give you more information on that on the end of my talk. So I will outline a bit what are alloying and tramp elements in steels, what is their origin, and how do they influence on a schematic level, basically our metallurgical processes. And then I give you an, let's say, fundamental research example from our institute where we investigate copper impurities in, let's say, industrial steels as well as in fundamental alloys to learn more about the precipitation behavior. And finally, I will give you an overview of case studies, which we did mostly with student theses, where we investigated, for example, standard steels like DC01, S355, and also in quench and tempering steel. And all of these steels were alloyed with additional amounts of tramp elements to more or less simulate future recycling steels, which we will produce more and more here in Europe. So let's start with the first topic, alloying and tramp elements in steels. As you all know, our matrix in steel consists of iron and carbon, but those materials I would call nowadays mostly boring if there's nothing else inside. So we have our alloying elements like chromium, manganese, nickel, silicon, and molybdenum. And every one of these alloying elements is always added with a specific aim in mind to increase strength, ductility, whatsoever. Besides these wanted elements, we also have impurities, either from processing or from raw materials. Also, we always have a certain amount of hydrogen in our steels, but most problematic are the so-called tramp elements. And the group I'm showing here, like copper, molybdenum, and so on, they are more problematic than the impurities from raw materials because it's really difficult to extract them from your liquid melt. So if they are once in your steel cycle, with every recycling step, you will enrich it and get more and more copper, for example. And over time, these copper additions can be really significant and will more or less destroy your steel concept. What's their origin? So when we are talking about the primary steel production, we have calcium, aluminium, phosphor, and sulfur, which come from raw materials, for example. They can be, as already said, removed relatively easily by metallurgical approaches. When we are then going to future steel production, for example, mixing DRI with a lot of scrap in an electric arc furnace, we will introduce tramp elements like copper or molybdenum, which are enriched in post-consumer scrap in our melt, and they cannot be removed very easily. There are some methods to extract, for example, copper. For example, vacuum distillation can remove a lot of the copper from the melt. However, all of these technologies which are available to reduce these tramp elements, they are very expensive, and you basically use your business case for steel production if you would use this for, let's say, standard steels for construction, for example. Additionally, we are talking also about nitrogen nowadays in Europe because a lot of steel concepts, especially for automotive industry, like bake hardening steels or interstitial free steels, they are very dependent on having high cleanliness and also, especially also low interstitials. And when we are now moving from a blast furnace-based steel production to an electric arc furnace-based steel production, these nitrogen levels are also increased and processes need to be adjusted more or less. When we are now thinking, okay, we have now different steels, or let's say similar steels, but with different concentrations of tramp elements on a thematically level, what would that change? So we can more or less summarize that copper, tin, nickel, chromium, molybdenum, and sulfur, all of them are reducing hot formability, cold formability, and they would increase strength slightly, mostly about solid solution hardening, and also toughness would be reduced. They originate from different scraps which are introduced into the general steel scrap. I gave some examples here, as you can see, especially when we are talking about bearings or high alloy tool steels, it becomes pretty clear why we're having also chromium and molybdenum in our steel script. So in a summary, most of these Tramp elements will, to some extent, increase the strength and limit the ductility. So with this, we could work to some extent. However, this is not everything which is covered by the Tramp elements, and we will, especially in the case of copper, see the biggest problem in the upcoming minutes. I already showed you an overview of the alloying elements in steels. I gave a small note in the top that this was, of course, incomplete, but I want to also give you another example, which is a bit less incomplete, because, of course, we also have microalloying elements, titanium, niobium, and vanadium, also nicely introduced by Anderson in the previous talk. What they can do, grain refinement, and other very interesting things, and more advanced steels. And also boron is alloyed, for example, in press hardening steels for automotive. And all of these steels here, all of these alloying elements, they are very, very dependent on the nitrogen concentration because they have a high affinity to nitrogen. And when we are moving in Europe to electric arc furnace-based steel production, all of the alloying concepts which are currently produced by the blast furnace, they need to be reassessed if they can be moved to the electric arc furnace. Okay, so far, a small introduction to the Tramp elements in general, where they come from. And now I want to go back a bit to what happens during phase transformation. And I will start with this equation here, the JAMAC equation, basically a standard equation for material engineers. And this gives you an idea about the phase transformation kinetics. So usually when we are talking about phase transformations, we are having a nucleation dominated area, a growth dominated area, and a saturation, so coarsening dominated area. And this is independent if it's a phase which is forming like austenite or ferrite or a precipitate. And what is most important, and I will give you some examples later, that all the impurities we just discussed about, they interact basically with these phase transformation kinetics. And this is what we need to consider, because these are the effects which go beyond only increasing strength or ductility. A more applied diagram, which can often be used, or which is often used in steel industry, are time transformation and time temperature transformation diagrams. We have here the perlite and bainite forming area. We have the martensite start temperature, and we have AC1, AC3, and the temperature for no recrystallization. And here we are seeing also schematically effects. So for example, our Tramp elements, they will move the perlite and the bainite field to the right, as all of these diffusion controlled phase transformations are usually delayed. We will have, in most cases, a reduction of the martensite start temperature, and also our temperature for no recrystallization is increased. And finally, AC1 and AC3 change independency of the Tramp elements. Why is this important? Because these diagrams are used to design every heat treatment process in the industry. And when we are looking now, based on these changes here, for example, on a typical quench and tempering process, here also schematically shown, we have influences on the austenitization temperature as A1, A3 are modified. We will have an influence on how fast we have to quench to achieve fully martensitic microstructure, because all of these phase fields are modified by the Tramp elements. And finally, we will also see an effect on the results we get after tempering, as carbide growth, for example, is also influenced by Tramp elements. This is for classic quench and tempering steels, maybe a forging product, but also when we are talking about thermomechanical road products, we have to assess the effect of Tramp elements. I already said that we will have an effect on the no recrystallization temperature, on the AR3 and AR1 temperature, and also our microalloying concept needs to be assessed, as we might have an interaction with nitrogen here. So basically, if your company is working with, is doing hot rolling, different types of it, normalized rolling, thermomechanical rolling, whatsoever, if Tramp element concentrations are growing, this needs to be considered and investigated how your processes need to be adjusted. From this fundamental basis, I would now like to dive deeply into one topic, which is the effect of kappa. And this is of, maybe the most prominent example, of course. It has been researched in the past quite extensively, but it gets more and more important because due to the electrification of the transport sector, more and more copper is entering the scrap cycle. So if you're looking on a standard gasoline car in the past, it had maybe around 20 kilograms of copper. When you now have a modern plug-in electric, it can have over 100 kilograms of copper. And just to give you an idea where all the copper sits, it's not only the motor for moving the car forward, also every quality of living improvement. For example, electric windows, they all contain small motors which contain copper. So all of this adds up in the end to a lot of copper which is introduced into our steel material flow. So we have to deal with it and also investigate what the copper is doing in the first place. As a material engineer, I really like copper because you can do a lot of it. You can improve strength, toughness, hardness. It influences transformation behavior. You get oxidation resistance and corrosion resistance, independency of the concentration. And most interestingly, there are a lot of studies in China. If you introduce quite an extensive amount of copper, you can even get antibacterial properties. So from this overview, you could say maybe copper introduced into the steel is not a bad thing. However, there's a big problem, which I will explain later on. Always, the impact is dependent on the steel grade. So which steel are we basically alloying with copper, the concentration of copper, and also the state. So is copper in precipitation or in solid solution? As a material engineer, I always go first to the phase diagram. And when I'm looking on the iron copper diagram, I can see that at low temperatures, we basically have a very limited solubility of copper, and thermocalc gives us here basically that we have ferrite and a copper FCC phase. From this, we can already more or less expect that we can use copper as precipitating strengthening element, and we can use it for tailoring the mechanical properties. As I already said, quite an extensive amount of research has been done in the past. And this is the current opinion in the literature, how the precipitation process goes on. So you start with a very high amount of iron still in your copper precipitate, and you have a coherent BCC precipitate, which over time develops over two semi-coherent intermediate states into the FCC thermodynamically stable incoherent copper precipitase. As indicated by the crystallographic strain, the FCC one has basically not much influence, and the BCC one is the most interesting one from a mechanical engineering perspective. This is only schematically, but as Anderson also nicely pointed out, we nowadays have possibilities to investigate copper on atomic resolution. And this is what we did in the past. So here you can see an atom probe tomography result. Basically, all these small orange dots you can see here are single copper atoms. And with these larger orange balls, we try to visualize copper precipitates. You can do more. You can then go very much into the material and investigate these precipitates also chemically. And what we can see, for example, here at this interface, which we visualized, we have a relatively large copper precipitate, which is already very, very high in copper. And the one in the matrix, not directly at the interface, they have a slightly reduced copper concentration, and also their size is, their thickness is approximately 50%. So you can already see in one sample, we have different types of precipitates, which are a bit contrary to what we learned basically on the schematic overview. When we are then diving further into the nanostructure, we can see that in the same sample, independent of the position, we can find BCC clusters, but also this intermediate precipitation states. And here we have a very nice image on the lower side where we could resolve the atomic structure. So we can see the precipitation process itself is not as easy as pointed out in most of the literature up to date. And when we are then not looking into ferritic steels only, but looking into more complex steels, for example, with cementite inside, we can see that the copper is precipitating in the matrix. You can see it in our EDS mapping here, but also it precipitates on the interface of the cementite and the ferrite matrix. And here we have a nice effect on the precipitation growth of the cementite. And this is one of the major effects which I wanted to point out at the beginning when we are talking about phase growth and the coarsening. So you could argue now, okay, how do these alloys or how do these precipitates really form? Basically, you can only learn this from in situ observation. And this is what we are basically working on at the moment. For this, we went to a synchrotron source for X-rays, and we did basically dilatometric investigations of our copper alloyed steels and measured the crystallography in situ. And basically, you can see here on this side our heat treatment and the change in length. And on the right side, you can see our X-rays results, which we collected during the quenching. And what we are seeing here is the main austenite peak. And during the quenching already, you can see that a small secondary peak is developing on the left of this main peak. Basically, while austenite is transforming into ferrite, you see a very, very small peak in the vicinity of the austenite peak. And this peak is basically FCC copper. And with this results, we could prove that in ferritic steels, you also have, in some cases, direct precipitation of this FCC copper. So we are a bit challenging here, what is currently more or less the state of the art. But of course, this is very important as all of our modeling approaches, they basically need this data to come up with predictions of how the copper precipitates are growing in your industrial steels. Finally, we could also demonstrate this again with atom probe tomography. So we did an investigation after 120 seconds ex situ and after 3000 seconds. And what you can nicely see, it's basically that you have a coarsening of the precipitates independency of your heat treatment time. Okay, from this we learn there are a lot of precipitates. It's a bit tricky to model them. It's a bit tricky to measure them. However, we can use them for strengthening. So what is the problem with copper? This we can also take from the phase diagram. When we are going to the bit copper-rich side and to higher temperatures, we can see that already above 1100 degrees, we have austenite and a liquid phase. This means that when you're doing your standard hot rolling, for example, at 1200 degrees, you might get liquid phases, and this will basically lead to catastrophic failure during your hot rolling. However, you might also ask, okay, this happens only if you are above 7.2%. Why is this an issue? So high will the copper not concentrate up in the steel scrap? This is true on the one hand. However, this is not a single problem of soluted copper in the matrix. The reason for this is that the copper-induced hot shortness, so the hot fracture of steel slabs, is a combined process of liquid metal embrittlement and selective oxidation. You start with an initial state where your copper is homogeneously distributed throughout the matrix. Then your scale layer will form, your oxide, and your copper is not soluble in the oxide. So your copper will enrich between the oxide and the matrix to such an extent that it will form more or less pure metallic copper. And when you then put a stress on the side, basically your copper can penetrate the grain boundaries very easily. This can be influenced, of course, either by working with other scale influencing elements like silicon, for example, or by working on the process parameters like the oxidation rate or the temperature. By this, you can push the copper a bit into the scale layer. However, it's still an issue which is not, let's say, completely understood. Some ways exist for working around it, but these ways are often defined only for a single steel, and the, let's say, mechanism behind it is still under investigation. Just to give you an example how this would look, in a steel sample, we did an interrupted hot tensile test, and here you can see nicely how basically the full surface of the sample is covered with deep cracks. And when you are then looking on microstructure images from the side, you can see that we have also penetration of this of these cracks into the steel sample. And when we are then looking into EDS mappings, we can see in this picture here that there is a lot of copper enrichment. So these are ongoing research at the Institute, especially to standardize the testing for the affinity to hot shortness and to give industry basically a way of finding out which copper concentrations are still possible to be produced in a certain steel grade. Okay, so far to the, let's say, more fundamental investigations. And now I would like to continue with some case studies on industrial steels. And I would like to continue with the master thesis of one of my students, Mr. Hinrichs. He investigated the 42 chromophore quench and tempering steel. And what we are doing, similar to what the colleagues at SENAI are doing, is we're usually producing our own lab melts up to 80 kilograms. And in this case, we varied the copper concentration and added 0.5 and 1% to it. And we investigated phase transformation behavior, mechanical properties, and also the hot shortness susceptibility. But I will focus here mostly on the phase transformation behavior and the mechanical properties. For this, we collected standard CCT diagrams. As you can see in this slide, we have here the reference state and then the CCT diagram for 0.5% and for 1% of copper. And as you can see here quite directly, but I'm adding a line here to make it even more visible, all of our diffusion controlled phase transformations are moved to the right side. So bainite formation is now taking place at slower cooling rates, the same as ferrite, and we couldn't even find any pearlite formation anymore. So we see here basically hardenability is increased through the 1% of copper. Additionally, we see that martensite start and martensite finish are reduced. And generally, we see a higher hardness independency of the copper concentration. However, for forging steels, this is not a bad thing, because when we increase the hardenability, theoretically, we could also produce components with larger wall thicknesses now from this steel and have a complete martensitic microstructure into the core, which might not have been possible without the copper. So, in my opinion, this would be a positive effect. When we are then investigating the mechanical properties, we can see here in the full line the reference alloy, and in the dotted line we can see the one with 1% of copper. We have differences independent of the tempering temperature, however not critical. And in general, we always have the, let's say, classic trade-off: higher hardness, lower ductility. Also, the general tensile test curves are quite similar. And the same can more or less be said for Sharpie tests. We can see that there is a general reduction in this case for the copper alloyed one. However, we are still for most tempering temperatures above the industrial threshold, which was defined here at 35 joules by our industrial partners. So also from this results, I would conclude that even 1% of copper can be tolerated in a 42 chromophore quench and tempering steel. The last finding, and this connects really well again back to the atom probe tomography, is the matrix increase, which we found in hardness, which we found at a certain tempering temperature. So as you can see here in blue, our copper containing steel has around 70%, 70 Vickers higher hardness. However, this cannot be explained by the solid solution hardening alone, as the solid solution hardening of copper is more or less around 10 to 20 Vickers in this concentration. But what we found when we looked into APT again is that the copper, here again in orange, connects up with cementite and other carbides. So the effect here of copper is not only that it adds by solid solution hardening, but it also interacts with the cementite and the other carbides, and more or less helps to keep them smaller, which is then effectively increasing the hardness more than it would be done only by solid solution hardening. So you see here a lot of interactions which have to be assessed, combined, to get the full picture. Continuing now with ferritic steels. First, we looked onto the Martensite ones, and now we are looking into two bachelor theses where we investigated industrial-produced DC01 and S355. So they were both produced by blast furnaces at the Salzgitter plant in Germany and artificially alloyed with Tramp elements to mimic a bit higher recycling fractions. And I will start with the tensile test of the S355. We had three different alloys here, two variants of S355 with slightly different carbon and manganese concentrations, and our reference steel somewhere in the middle. And what I want to point out here is not really strength and ductility, because this changes very much, of course, with the carbon and the manganese concentrations. But what you can see is that we have a pronounced yielding here in this steel. So this is connected also to higher nitrogen concentrations, which I pointed out in the beginning of the talk. Similar things were found for the DC01 and the DD11 variants, so the hot rolled and the cold rolled state. Also here, we could find an pronounced yielding in the green steel, So this needs to be considered. Maybe not the properties itself will be affected, but the deformation behavior on a more abstract level. Besides the tensile test, we also looked into hole expansion ratio, to be honest, on relative thick material. However, we still wanted to investigate this. And what we could find out is for the S355 that the green steel, due to the higher amount of impurities, achieved smaller hole expansion ratios. This was more or less as expected. However, when we looked then onto the deep drawing steel, we could see that here our hole expansion ratio was increased, even with the higher strength and the introduced Tramp elements. The reason for this was then connected basically to the microstructure. We did a thorough investigation of the grain size distribution, and what we could find out for both steels is that the green steel variants had a much smaller grain size due to the solid drag effect of the Tramp elements, which prevent basically the coarsening of the ferrite during the batch annealing. This also fits very nicely back to the beginning of the talk. Here you are seeing now basically a more schematized drawing of the recrystallized ferrite fraction in our steel grades, and what is basically happening when we add Tramp elements. So when we are looking on recycling steel grades, this recrystallization is shifted to longer times, and this can be assessed, and we can work against this by adapting process parameters, for example. So to summarize basically on the case studies, in most cases, we can say that by adjusting the process parameters, for example, heat treatments or rolling parameters, we can really work on adjusting our steel properties that we achieve more or less the same than before. Of course, there are some major issues like hot shortness, but these can be also assessed, and we are pretty sure that we can adjust our steel products in the future to go to a more sustainable and more circular economy oriented steel production. To close my talk, a small advertisement. We recently started our graduate school on this topic. It's funded by the German Science Foundation. We have 24 parallel PhD students working on this for 5 plus hopefully 4 years. It started this April, and we are working on the complete production chain. So from iron and steel production, steel processing, steel application, and also sustainability assessment of the full production chain. And we are hoping to address these topics with this large project in a very holistic way. If you want to follow us on LinkedIn, you are, of course, invited to scan the QR code. With this, I'm at the end of my talk. Thank you very much for the attention, and I'm looking forward to questions in the end.
Thank you, Professor Dr. Alexander Gramlich, for your excellent presentation and valuable contribution. We will now continue with our program. It's my pleasure to introduce our next speaker, Dr. Vicente Trindade, who will present strain and age aspect during relay operation of Linepipe. Dr. Vicente Trindade holds a PhD in Material Science from the University of Siegen in Germany. He has over 20 years of experience in industrial research and development, focused on steel development and industrialization. He is the author of 6 books and more than 130 scientific papers published in peer-reviewed journals and has co-supervised numbers of master's and PhD students. He currently serves as R&D Director at Vallourec South America. Vicente Trindade, the floor is yours. Please go ahead and begin your presentation. You have 30 minutes. Have an excellent presentation.
Okay. So thank you very much. Hello, everyone. So first of all, I would like to thank the SENAI in name of Anderson and Denise for the invitation today. And of course, I would like to thank my colleague, Diego Araújo Santana, who really conduct this study along these last months. And I want to say that Vallourec really appreciate the high level of technological and scientific long-last partnership with SENAI, which is very close here to our plant in Brazil. So my talk today, it will be about strain and age aspect to the relay operation of Linepipe. So I'm going to talk about steel application on the oil and gas industry. Let's move here. So the agenda of this talk will be more or less like a brief introduction about the Linepipe application, about relay and strain age process, and then we come to mechanical properties, strain and age mechanism, and go to which material we are going to show you in this third case, and microstructural characterization, the final remarks. So as introduction, I'm going to talk about seamless pipe for offshore application. So in the oil and gas industry, we have basically 2 big class of material of steel application. One we call OCTG, oil country tubular goods, are pipes used to extract the petroleum, the oil and gas. So it's the oil and gas production. Usually they are steel with medium carbon and they are not welded. They are connected by threaded connections. On the other hand, we need pipe to transport the oil and gas. Okay, so and this pipe are we call line pipe steels, and they are applied in rush environment in most of the case. So usually these kind of steel are low carbon steels because it's mandatory to have a very good weldability. They are low alloy steels. They have to have high strength and excellent toughness, and they have to they are submitted to H2S environment. They have to be resistant to H2S environment and also fatigue resistance. So today I'm going to show you one example of this class of material, line pipe. So I'm not going to talk about the behavior of the OCTG, but line pipe material. So one aspect of line pipe material is that when we are talk about offshore application, we need to deploy this steel, the pipeline. And there are basically 3 technological method to do that. The two first one is so-called S-lay or J-lay. So it means the single pipe length, usually the pipe length are 12-meter pipe. They are transported by vessel to offshore place. And there in the offshore, those pipes are welded to each other, girth weld. And those pipe then, those pipeline are then laid in the ocean. Okay, so the characteristic of this process is that during the laying process, those pipes are not submitted to severe plastic deformation. And the process, the laying process or the deformation process is low. Okay, good. This is one technology very used in the market. Okay, the another one, very important one, is the relay process. So it means in this technology, the pipes are welded in onshore, so inland. Then we do a lot of rack of pipeline, and those pipeline are then connect together and then reel here in big reel drum. So the pipe are really real, okay, this here. And during this process, you can see here in the real photo. So here is the reel drum, and the pipe are then real in this equipment. So you can imagine the severe plastic deformation suffered by these steel pipes. So this vessel is then transported to the offshore place, and then the process need to be now done in the way to unreel those pipeline, and then you need those pipe goes to different condition of plastic deformation. So this is a very interesting process because this is very fast compared to the previous one, and it's cheaper than the previous one, but this require a high, I'd say, performance of the steel, because they are suffering severe plastic deformation during reeling and during unreal condition. So now the question is, when you lay the pipe in the sea, those pipe will have some remain plastic deformation, and with the time, do you have aging effect? What happened with the properties of this material during the life cycle of this pipe, which is around 20 years? Okay. So during this 20 years, what happened with this pipe that was laid with some remain plastic deformation? So the industry has a way to evaluate it, of course, before laying. We have actually two methods to evaluate it. One is to use, we call a small scale healing test. I show you next line, how we can simulate this in the lab, and also full scale healing. So we expect, so from the material science, that the seamless pipe are produced hot hole and followed by heat treatment, which is quenched and tempered. So those pipe, if you have these properties, when we have some straining of the pipe, some remain plastic deformation, probably we have a work hardening and aging hardening. So this is if you have a plastic deformation in tension, but you can have also part of the pipe have some compression strains. So in this we can have a contrary effect we call Bauchigen softening, but we aging can even always happen. Can always happen. Okay, so this is what we are going to investigate in this study. Okay, so just to have an overview what happened. So if you have here the real drum, and here is the pipe. When you are healing, so you have part of the pipe. So if you look here, so let's call here this part of the pipe as 12 o'clock and here 6 o'clock. So if you analyze the stress strain curve, submit to this pipe during reeling, so we can see at this position, so at 12 o'clock you have a tension, and at 6 o'clock you have compression during reeling. So during unreeling or reeling off is the contrary. So at 12 o'clock we are going to have compression, and at the 6 o'clock we are going to have tension. So and so on. So of course, when we are reeling, you can see here that the pipe goes to this aligner device and then straighten the device. So we can analyze, we can imagine, so I can show you in this diagram, this Caires diagram, that for each part of the operation, the pipe are suffering different cycle of straining. So here's one example. So on the right-hand side, you can see how we do full-scale reeling. So we can do this operation in the lab. So although a big lab, so we use full-scale pipe or full-length pipe, we can simulate a different deformation cycle that is submitted during reeling operation in the offshore engineering. So after that, this is one possibility to test the material before putting service. Another way is to use the small scale healing. Small scale healing is much simple to do because we just take some specimen like this. So like it's the tensile testing, tensile specimen, and then we can use a laboratory machine and do the compression and tension cycle as we want here in this machine. So we can simulate it in the lab, use full scale, full pipe, or use lab tensile test machine, okay, with different cycle of compression and tension. So when we are doing this kind of reeling, so we start to do the when we introduce plastic deformation, we interrupt, like we are interrupt the tensile test. So, and then if we continue with this tensile test, the behavior will be like that. Okay, so during, let's take a quench temper material. This will be the behavior of a quench temper low carbon steel. So, but if we interrupt the test here, so the material have some remain plastic deformation. If we submit it to aging, so what we observe, the curve now is like this. So we have an increase on the strength. So in this increase, you have an increase due to work hardening, so introduced by the dislocation density, plus one delta, which is attributed to the aging effect. So this is what we are going to discuss in more detail, the contribution of this work hardening and the contribution of this aging effect. So like this, so just summarize the total strength, in this case, the YS of the final material that is really on the C is a contribution of the work hardening plus aging. So when we are looking to the aging contribution, we can imagine two contributions. One, due to the dislocation pinning, formation of the cotral atmosphere, we are going to discuss a little bit about it, and the precipitation hardening. So we are come back to here, to this mechanism, okay, to see which one will be more important in this aspect. So here, just to give you a idea that that the material properties really affected by the reeling process. So you can see in this diagram the hardness, the effect on the hardness. Here is the Vickers, HB10. So here is the I would say as received materials, as heat-treated material, quench and temper material in this hardness level. So, and A, B, C, D, E represent different kind of reeling cycle. It's a combination of compression and tension, different cycle. But here we are from A to E, we are increase the final plastic deformation and the intention. We can clearly see that indeed the hardness is affected considerably as we increase the final plastic deformation. This happened for hardness and happened also for the strength. YS, you can see the YS increasing and the UTS as well, and the toughness measured by absorbed impact energy. You can see that the toughness decrease considerably when we go to aging, after aging of those material. So what is quite interesting to observe, so I will not demonstrate here, but you have to believe me, that the cycle number C and D, so D and E are not cyclic, they are just strained by monotonic force, stress, okay, just a monotonic, like a single tensile test, and the A, B, C are cycle, so different number of cycle. So, but what we can see that C, D, at the end of C, we are going to have around 2.5% of remain deformation, plastic deformation, and D also 2.5. Independent, if one is monotonic or C is not monotonic, is cyclic, we have at the end similar or same behavior. Okay, this is a very important conclusion for the industry. So that means if you want to simulate, and we do it in the routine to simulate the cycle of the Rio drum. If we do monotonic simulation or cyclic simulation, it seems to be same behavior. What matters is not the number of cycles, but what matters is the final deformation, plastic deformation that remain in the pipe. Here, another very important finding, and for the industry, is that, as I told you, the increase on the strength, we should have two contributions, one from the work hardening and another one coming from the aging process. When we see the contribution of each one individually, we can see that the increase in the strength by work hardness is much more significant than that increase from the aging process. You can see, okay, let's say in general, we are talking about 70% of the increase is due to the work hardness, and let's say 30% is due to the aging. This is another important thing. So for the industry. Good, this is fact. Okay, this is observation, experimental observation in the extensive lab tests. So what are the fundamentals for that? So we know that when we introduce plastic deformation in the steel, of course, we create defect, and one of these defects, very important, is dislocation, right? So you increase the dislocation density of the material, and if you submit this material to aging, so we create mobility of the atoms, and then you of course are going to have diffusion, mobility of interchange tissue atom, of vacuums, and substitutional atoms. So this should happen in the material. So plastic deformation create dislocation, defect, and aging. During aging, atoms mobility should happen. It's very well known in the literature, of course. So all of you know that work hardening is due to the increase of dislocation density. So as when we increase the dislocation density, we increase the hardening effect. So this is very well known. And aging, so the product standard defined in their specification, product specification. For example, if you take DNV specification or API specification, they recommend to evaluate the aging of the material by use a temperature of 250 degrees Celsius for 1 hour. So you have to deform your material in the deformation grade that you want. And then after deformation, you need to submit your material to aging, which is 250, 1 hour. So if you if you make some simulation and pay attention to the intertissue atoms in steel, which is more important than carbon and nitrogen, you can see that indeed at 250, 1 hour, so those elements, small elements, they can really have some mobility in the crystal structure about 10 micrometer diffusion distance. And this is enough. This is enough to reach the dislocation core and saturate those dislocation core. So this is one important saying. The second point is, okay, if you analyze the diffusion of substitutional, like manganese, molybdenum, vanadium, niobium, for example, so at 250 degrees Celsius, if you look to the mobility, is almost nothing, okay, in terms of diffusion distance. So after 1 hour at 250, the distance, the diffusion distance, here we have data from literature, 300 degrees Celsius and 500 degrees Celsius. In the ferrite, it will be around 1 angstrom. So it's nothing. So so what we can say here, what I want to tell you, is that during aging, most probably the substitutional element has absolutely nothing to do with aging, but only the intertissue, because they indeed has ability to reach, to travel, to diffuse up to the dislocation core and saturate it, okay? And this is what come to the important phenomenon, which is the Cottrell atmosphere formation. And so we know that when those elements, the free intertissue atoms like carbon, nitrogen, they tend so to diffuse to areas, to region where you have dislocation, trying to lower the strain energy of the system. So, and then those elements will diffuse towards those areas, those regions, dislocation core, and saturate it. So, for example, just as example, we just need 1 ppm of carbon to saturate a dislocation dense of this level. So we need a few amount of element to form the Cottrell atmosphere. Once we have this saturation, we have now a phenomenon called pinning of dislocation by Cottrell atmosphere. This is what happened during the aging. So the Cottrell atmosphere is pinning the dislocation movement and then increase the material strength. So just one example. So let's take this material, very common material in line pipe. So as I told you, it's low carbon, okay, because we need good weldability. So of course, we have nitrogen on those elements, and we have the alloy element added intentionally, okay? So, and of course, probably, as Dr. Gramlich showed before, we should have some Tramp element also, but it's not studied here. In this case, Dr. Gramlich, molybdenum is not our Tramp element. Molybdenum is our design element, okay? So, okay, just comment aside. So what we have here, I'm going to show you in the next few minutes, is the behavior of this steel in the as a received condition, as quench and tempering condition, after straining and after aging at 250 for 1 hour, as recommended by the product standard in the industry. So the first finding, so we use different technique to study this material. So use SEM, for example. So we could not see any change in the microstructure when we compare all the three conditions. So the final microstructure after heat treatment of such a low carbon steel are bainite microstructure, and this bainite microstructure remain as strain and strainage. There is no significant or no change in the microstructure. If you go even use other advanced technique like EBSD, so we can also confirm that there is no change in the grain size of the material, and also no change in the bainite microstructure as already observed in the simpler SEM microstructure observation. So, and then if we want to go in more detail in the microstructure and to observe the micro precipitate, so we need to go further in the advanced technique which we use here is TM, transmission electron microscope. And in this transmission electron microscope, what we could observe also is that independent on the condition as received, as straining and the strain aging, the precipitate observed are basically the same. There is no change on these three conditions. So, and also here you can see just as illustration when we take this selected area of the diffraction pattern, use TM, so we see clearly the ferrite pattern and also the diffraction spot from cementite. In this case, this cementite crystal size are around 200 nanometer, just as information. Okay, so when we not validate, but we compare with what the observation shows, and compare with the thermodynamic calculation. And so in this case, we use thermocalc software, so we can see that at this low temperature region where the material is submitted to tempering and submitted to aging, 250, the expected thermodynamic precipitate are exactly close to what we have observed in the experimental study. So additionally, you can hear cementite. So just additional, so cementite here is really as observed. We have observed cementite, which is with very rich in manganese atoms, a solid solution. So as thermodynamic also predict this high solubility of manganese in the cementite. So just as curiosity. So we also went to more advanced technique to try to identify more and more smaller precipitate. We use high energy X-ray diffraction. Here in Brazil, we have this facility. So So this facility is located in the São Paulo state. So in Campinas is the city, and the research center is called CNP, Centro Nacional de Pesquisa e Energia e Materiais. And there we use this facility to investigate our material in different conditions as QT, as quench and temporary, straining, and after aging. And what we could observe is, again, nothing, no big change in precipitation. So all the precipitate are basically the same. The only highlight we can say here is that when we observe here the cementite peak, we can see that this blue curve here is for the SQT. You can see this sharp peak. And then after that, this orange here is the as strain. Then you have a more, I would say, broader peak as expected, because you introduce some macro deformation. And then when we after aging, what we could see that this peak become again sharp. Okay, so this is the only observation that we could extract from this technique, plus the observation that no change in the precipitation, macro precipitation. So based on all this in the theory and based on our experimental observation, we could conclude that work hardness is, of course, it's very important. The most important increase in the strength after strain and age is due to the work hardness, around 70, 80%. The other 30, 20% is due to aging. What we could demonstrate is that this aging most probably is not dominated by precipitate hardening, because we could not identify any big difference of the precipitation pattern after aging, but most probably the aging is basically there's a contribution with this location pinning. I mean, the Cottrell atmosphere saturation. So now I come to the conclusion, my final slide. So use advanced characterization technique include SEM, EBSD, TM, and high energy X-ray. It was demonstrated that no significant microstructural change occurred between the as strain and age condition. In particular, no evidence was found for the formation of a substantial amount of fine precipitate that occurred that could account for the observed straining. This find indicate that the contribution of aging is most likely associated with Cottrell-Pini effect. So furthermore, Cottrell-Pini is governed by the presence of the free interstitial carbon and nitrogen atoms. So, and finally, work hardness appear to be the dominant straining mechanism in Linepipe steel when subject to the strain and aging process. And the change in mechanical behavior are independent of the number of loading cycle and depend solely on the final accumulated plastic strain. I think this is my contribution for the talk today. I really appreciate the presence of all of you. And I'm open for any contact from you for further question, further explanation. You can send me an email or send an email to my colleague, Diego Araújo. So I appreciate and thank you very much for your presence. Back to you, Grace.
Thank you, Vicente. Thank you, Vicente, for your excellent presentation. We will now begin the Q&A session. Please submit your question, use the YouTube chat. Anderson, we will start with the question addressed to you, okay? The first question is, you should some images with microscale with martensite and the other phases identified. What that identification and assignments done automatically? If so, what method and the software reused?
So nice. First of all, congratulations for Alexander and Vicente for really nice presentation. So I learned a lot in these lectures here. So great presentations. So thank you for the questions. And as part of not, identification was not automatically. Our phase identification was manually by the analysts and combine morphological criteria and response for each constituting to a specific chemical action. So, but nowadays, I was studying AI-based approach for automatic phase segmentation and quantifications here our marketing departments, and actively looking for academic and industrial partners for create and validate these algorithms for steel microstructures together use. But for now, we have not using an automatic algorithms for identification. Thank you. Great questions.
Okay. Thank you, Anderson, for your nice contribution. The second question is, what are the most requested characterization techniques in the industry nowadays? One section. Second, is it more usual for company to use the price of a large project or contract, or to they buy the ad hoc one-off sales? Also, what is more common at SENAI?
Oh, this is a nice question. So, okay, for the most requested characterization techniques in our lab here at CIT is metallographic characterization. So, sample preparation, selective actions, chemical actions, and analysis by optical and SEM for maybe for phase identification, grain size, including something like that. For ancient for most quality and value analysis questions. So because it's quickly and low cost, but X-age fractions and coming next because the phase identifications are really important, and crystallographic texture sometimes in residual stress measurements is really common here in our laboratory. And then next we have the transmission at the microscope for more big problems, for questions, and especially for analyze nanoprecipitations and dislocations, structures, and interface. I think it's more common using GEM. But for the second questions, okay, both happen, okay, but these have different approach. So here at CIT, we have a dedicated team for service for industry, for more common questions, and a company need for a very fast and objective answer. And okay, it's a very, very fast. It's a service for us. We have a dedicated team for this, but our core business is RID projects. Together is a companies in Brazil. We have a dedicated team for RID for industrial projects together for our colleagues like Vallourec, for example, is a great partner for us here at SENAI. Thank you for the great questions, and I invite you to know a little bit more our approach to trying to resolve your challenges. Thank you.
Thank you, Anderson, for your nice contribution. Daisy?
Okay.
Okay.
Professor Alexander Gramlich. We will now continue with the question addressed to you. The first question is, Alexander, I didn't understand the effect of copper in the oxide layer. Copper is an element with improved the oxide layer resistance, but during the hot holding, copper can penetrate in grain boundaries.
Yeah, thank you for this great question. I will take some time to explain it a bit more in detail. So basically what is happening is that the oxide is growing, but more or less copper is so noble that it will not oxidize because you have a lot of less noble elements like iron, which will form the oxide layer step by step. And this will mean that the copper stays basically at the matrix oxide interface. I guess that Dr. Trindade is a much more better expert on high temperature corrosion, as I just learned. So I guess he's also quite familiar with these topics. However, basically you then have your copper at the interface. And if we are at comparatively high temperatures, it will become liquid because the melting point of copper is comparatively low. And when this happens, it can basically penetrate the grain boundaries and weaken the cohesive forces. And by this, if you then pull on the steel, you can separate the parts very easily.
Okay. Thank you, Professor Alexander, for your valuable contribution for us. We have two questions for you. The second is, how can silicon be used to minimize the hot shortness for these EAF steels made from recycled scrap? Do we have any radio with copper that can avoid cracks?
So this is also two very interesting questions. So these are relatively new results which we are investigating currently. So what we are seeing in silicon alloyed steels in these 42 chromophore, but also, for example, we have some trials with electric sheets, so very high silicon concentration, that apparently the internal oxidation is interacting with the copper precipitation. So you have silicon oxides which form around grain boundaries, and from our initial SEM observations, it looks like they will put more or less compressive stresses onto the grain boundaries which prevent somehow further penetration of the copper. And additionally, in these steels, you anyway have internal oxidation, so you are anyway need to ground away or machine away the surface. And then basically your loss of surface is defined by the internal oxidation and not by the copper precipitation. In terms of ratio, silicon copper, this is what we're looking in at the moment. I don't have any results on that, but in the 42 chromophore steel, the silicon ratio is quite low. In general, we see the cracks above 0.15% of copper. So this was investigated in the past, I think like 30 years ago already, that when you are in low alloyed steels, everything which is above 0.15%, you start getting surface cracks. And below that, it's usually fine.
Okay, thank you, Alexander. The last question is, how can CALFAT-based simulations and kinetic models support the prediction and control of Tramp elements in steel production and automotive steel development?
Yep. Also very good question. So especially when we are going for multi-phase steels, the development of the different phases, retained austenite, martensite, bainite, and so on, this is really delicate. And if we have a lot of Tramp element inside, all of these processes, they basically need to be reassessed. And of course, you can do this with a lot of experiments and trials. However, it would be, at least to our understanding, much more straightforward to have some supporting points and then interpolate basically in between these points based on CALFAT simulations, also using phase field approaches and so on. However, we are in contact with the Thermocal colleagues, also with other companies like GTT, who are distributing FactSage and so on, and all basically are saying that database development is also necessary at the moment. So this is something which is done, I think, at these simulation companies. But yeah, we will see more and better databases coming up in the future, I guess.
Thank you, Professor, for your excellent answer and contribution today. Now, Eduardo.
Vicente, we will now move on to questions for you.
Okay, take it easy. Only easy question, please.
The first question is, what are the critical differences between strain aging effects observed after relay installation and those occurring during conventional pipeline manufacturing process?
Well, so what our industry try to do is to replicate, try to understand what happened in the, so we cannot wait 20 years to see the effect of the aging of the pipeline in the offshore. So we have to simulate in the lab. So what we take into account is what is the predict strain during laying process and replicate it in the lab. So this is what is done. So, and this is the product standard, like DNV, for example, establish that we need to use a straining followed by aging of 250 1 hour, which should represent a critical, I would say, the most critical situation where you have all the complete saturation of its locations core. So this is the critical situation. So we understand when we simulate in the lab, we are simulating the most critical possible situation where we have all saturation done of the dislocation.
Okay, thank you for your great answer. The next question is, during relay installation, steel undergo multiplied for deformation cycles. How does the cycle plastics deformation modify the dislocation structure and affect subsequent mechanical behavior?
Yeah, correct. So this I think this was interesting to find that I tried to communicate today, so that independent of the amount of cycle, compression, tension, compression, what is important is the last cycle. What is the last cycle deformation? That this is which is account for the final mechanical property change. This is yeah. So the number of cycle seems to be I would say no big effect. Okay. So
Okay.
the most important is the final. If you do monotonic deformation or cycle deformation, it doesn't matter. Okay, for the final mechanical properties.
Okay. Thank you, Vicente, for your valuable contribution. Any questions that can be answered during this section will be forwarded to our speakers, and the responses will be sent by email to our webinar participants at a later time. Casey.
We are now coming to the end of today's webinar. I didn't get send the link of the survey link in the chat, but I will send after by email for all of them of you guys. We'd also like to thank all of our speakers for their excellent presentation, and thank all of you for joining us today, for your interest and for your questions and participation throughout the webinar. It has been a pleasure having you with us. Thank you very much for joining us, and we look forward to seeing you again at our next webinar. Have a wonderful day, guys. Bye-bye.
Thank you.